So in our last lesson, I talked to you about what are complex ions. And we're going to look at calculations involving complex ions because this is another environment in which equilibria can play a role. Here is the formation of a complex ion. The complex ion is COCl4. Now, we talked about how the cobalt central atom has got a positive charge, and the chlorides are donating an electron around it to form that ion. Well, as with any equilibrium, you can write an equilibrium constant expression. And so you see it written out there in your screen. Remember, you include anything that's aqueous, so there's nothing to leave out in this case, is there? And you raise to the power of their coefficient. I only have one coefficient, it's 4. So products over reactants raised to the power of their coefficient. Now we have a new subscript. The new subscript is an F. What does F stand for? It stands for formation. So you're forming a complex ion. Well, if you're forming it, where would you write it? It is written as a product. So you're making the complex ion. You are forming the complex ion. What are you forming it from? The central metal and the ligands that surround it. And that is what the F stands for, the formation of that. Now, these values are generally quite large, where when we were talking about KSPs, we had very tiny values, and the equilibrium lied far to the left. These are quite large, and these equilibria lie far to the right. Now, they're still equilibria, so there's still some of everything present, but you have way more product than you have reactant. This is going to lead us to do problems a little bit differently. When you have very small values, you can make some assumptions and it makes it easier. When you have really large values, we're going to make a new level of assumptions, a completely different level of assumption. The best way to show you how to do this is by way of an example, okay? And I'll talk you through why we're doing what we're doing as we work on this example. We are going to form a complex ion, and at the very bottom of this problem it tells you what the complex ion you're forming is. Since you're forming it, you have to be able to write your own reaction. You put it on the right hand side. So there is a complex ion that contains 4 of these ammonia molecules, and overall it has a 2+ charge. That is a complex ion. What do we form it from? We form it from the central metal. Copper has a 2+ charge, that's its central metal cation, and it has 4 ammonia molecules. Ammonia is a neutral molecule, and there is the reaction. That's the first thing that you have to be able to do. Write what you're forming on the right, the central metal and the ligands that formed it on the left. Now I'm going to leave room for a table, and I'm going to go ahead and write the K, and it's an F because we're forming, that's the name of this guy, would be the copper ammonium complex, copper ammonia complex. Why did I put a 3 there? I have no idea. The 3 is supposed to go there, and a 4 is supposed to go there. Divided by the copper concentration times the ammonia concentration raised to the 4th power. And the KF I gave you, it's equal to, this guy is equal to 5.0 times 10 to the 13. I told you they were quite large. That indeed is a very, very large number. Okay, now, what is the thing that I have to do that's different to handle calculations of this kind? I could do an ICE table, and I could do -x plus 4x and raise 4x to the 4th power. I'm going to tell you that's going to make it very complicated to solve. But there is an assumption that we can make. You see what I put there? An F instead of an E. What I'm going to do is an ICF table, final, because this goes nearly to completion. So it's as if it did go to completion, and then at the end I'm going to say, well, it almost does, and I'll show you the modification at the end, okay? So what do we put into an ICF table? We put moles. and not molarity into this table. So I need to go about figuring out the moles that I can plug in here. Now before the reaction is forming, there isn't anything there. That one's easy enough. But let's go ahead and calculate. And I'm going to do this again down here on the bottom left, okay? And let me get my papers here so I don't mess up any of the numbers. To get the moles of copper, what is my source of copper? When I look at the problem, it's copper sulfate. I have 2.50 grams of copper sulfate, right? I need to know when I have this dissolved, I know there's some copper ions floating around and some sulfate ions floating around. I don't care about the sulfate ions, but I do care about the copper ions. And I want to know how many moles. So how do I go from grams to moles of copper sulfate? This is grams of copper sulfate, so I need the molar mass of the whole thing in order to get the moles of copper sulfate. Now, I earlier did the calculation of the molar mass of this, and it's 159.61 grams per mole. And that is going to give me a value of the moles of copper sulfate of 0.01566. Now, this is moles of copper sulfate. I want just moles of copper. Look at that. How many moles of copper are in every mole of copper sulfate? 1. So this is also the moles of just copper. And I can put that into my table, 0.01566. All right, now we're ready for ammonia. To get moles of ammonia, what's my source of ammonia? Well, it's a solution. It tells me the molarity and the volume of that solution. The molarity was 0.3. I know molarity is moles per liter. So if I multiply by how many liters I have, it says that I've got what? 900 milliliters. That's 0.9 liters. Okay? And that's going to give me 0.27 moles of ammonia. Okay? Molarity times volume will give me the moles of that. And I can put 0.27 here. Okay. So now we have got ourselves the first line. Now, in an ICF table, what we say is this reaction goes to completion. With such a large K, it nearly does. So let's assume that it does to begin with. We look at our balanced equation, we look at what we have number-wise, and we say, which one is going to get consumed completely? Well, it's going to be this one. When I subtract 0.01566, it's going to get completely used up, and it's essentially or nearly 0. We're going to learn it's not exactly. And what do we go under here? Well, I'm going to do 4 times that number. Where did that 4 come from? Came from the balanced equation, right? So this is going to be consuming 4 times that amount, and I'm going to produce 0.01566 of this, because for every one of those that I react, I make one of those. When I subtract these values, I get, well, it's still going to have some left, carrying a little extra sig figs along for the ride right there, and I'm going to have 0.01566. So there's my F line. Now, keep in mind that this is in moles. What do I plug into here? Not moles, molarity. Now, here is the modification. We subtracted it and we said it's 0. But this is not going to completion, it's going nearly to completion. So it's not really 0, there is going to be some there. We're going to come down here and we're going to figure out how much is actually there. So we're going to plug in what we know. Kf, which is 5.0 times 10 to the 13, is equal to the concentration of this. What's the concentration of this? Well, it's the moles, 0.01566. That's the moles, divided by the volume. I have 0.9 liters. So that would give me the concentration of that guy. The concentration of copper, that's what I'm trying to determine. I know these guys' concentration. Let's get the concentration of the copper. I don't know it yet. Concentration of the ammonia is its moles, which was 0.207, divided by its liters. They're both in the same container. They're both 9 liters. And that's raised to the 4th power. And now I can solve for copper. How would I solve for copper? Well, copper's concentration is going to be, bring it up here. When I divide those numbers, I have 0.0174. I'm going to divide the 5 times 10 to the minus 13 to this side. And I'm going to divide these and raise it to the 4th power. It's 0.2304 to the 4th power. So the copper concentration is 1.2 times 10 to the minus 13. So I ask you, is it 0? No. Is it essentially 0? Yes. So if you have a problem where you're trying to calculate the concentration of everything in solution, once the equilibrium is established, we know the concentration of the copper ammonia complex is this number. We know the concentration of the ammonia is this number because that's the moles divided by the liter. And we solve for the concentration that's almost non-existent, and that gives me the concentration, and let's give it a unit of that. Okay, so we have our first complex ion formation problem. It is a modified ICF table. It really is a full ICF table, but at the end we say it really isn't 0, and let's figure out what its concentration is. Our next problem, and we see it down there at the very bottom of the screen, involves taking some cadmium nitrate, 5 or 0.5 grams of cadmium nitrate, and dissolving it into some sodium cyanide solution and forming, can you see the complex ion forming there? The cadmium cyanide is CnCN4 with a 2- charge. So that's what's going on. Now, as in this problem, the first starting point is really the hardest part. The first starting point is to write a good reaction. So I want you to first decide which one of those reactions would be the one that you would write down for the information given. And as a hint, remember, you are forming the complex ion. All right, so did you, oops, I did not go there. I thought I had a check mark there. All right, so did you pick A? That would be the right one. You are forming, it is on the product side. You are forming the complex ion of the cadmium cyanide complex from the central metal of cadmium and 4 of the ligands that are the Cn- problem. So when we come back, we're going to have our board erased and we're going to be able to work through this problem. Now this is not complicated, but we have students that really struggle with this because it comes in a series of a bunch of other stuff, and keeping it all straight is where the challenge lies. We are forming a complex ion, so we have our reaction of the formation of this ion. What are we forming it from? We're forming it from its central metal ion, which is C. Ooh, I don't like the way this pen is writing. Hang on a second, let me get a different one. We have the cadmium, and it's got a 2+ charge. And we have 4 of the ligands with their minus charge. Now everything is aqueous, right? AQ, AQ. Now we're going to leave room, and because of the magnitude of the KF, and you see what it is, 3 times 10 to the 18, we're going to run with an ICF table. We're going to assume that it goes to completion and then take into account at the very end that it didn't exactly go to completion. Okay? Now we're going to write the expression, KF, which the value is 3 times 10 to the 18, is equal to the product, cadmium CN4 with a 2- charge, over the reactants. Okay, the reactants are cadmium with a 2+ charge and cyanide minus with raised to the 4th power. Okay, so there it is, ready for us to do eventually. Now, if it's an ICF table, we don't put in molarity, we put in moles. We need to know the moles of everything. In the I line, we haven't formed any yet, so there's definitely a 0 there. To get the moles, and I'll come over here and work on the moles, I need to get the moles of cadmium. And I look over there and I say, what's my source of cadmium? Well, my source of cadmium is the cadmium nitrate. And they tell me that I have 0.5 grams of cadmium nitrate. Well, I need moles. So I'm going from grams to moles using the molar mass of the cadmium nitrate. That's going to give me the moles of cadmium nitrate. So the molar mass of cadmium nitrate is 236.42. Okay? And that, when I divide by this number, is going to give me the moles of cadmium nitrate, which is 0.002, and I think I have a couple ones, yes. And that's going to be the moles of cadmium nitrate. Now look at that formula for cadmium nitrate. How many cadmiums are in it? There's only one. So for every cadmium nitrate, there's going to be that many cadmiums. So it's the same number, 0.00211. Let's pretend for a moment. What if the formula was CD2? What if there's a 2 right there? Well, then it would be double this because there's 2 cadmiums in every one of these. But that right there is a 1. All right. Now we need the moles of the lichen, which is Cn-. What's my source of Cn-? Well, it's a solution of sodium cyanide. It is 0.5 moles of sodium cyanide per liter. That's the molarity. If I took that and multiplied by the volume, which I have 500 milliliters, that's 0.5 liters, I end up with 0.25 moles of sodium cyanide. What part of that do I need? The cyanide. So if this is how many moles of sodium cyanide I have, how many moles of just of cyanide do I have? Well, it's the same number. So I 0.25. I don't multiply it by 4. These coefficients come into play when the reaction takes place in the change line. This is just what I've dumped in. This is what I have initially. Now I'm ready to do the change line. We react the smaller. So if I react all of this, I'm left with 0. And we know that it's close to 0. It's almost 0. And we'll see that it's not exactly 0. Then I want to subtract 4 times the 0.00211. And I'm going to produce 0.00211. So this is going to give me 0.25 minus this number is 0.24. I'm going to carry an extra sig fig. That's moles of this guy. Okay, and then this is obviously going to be 0.00211, and this is moles. The problem says, tell me, once this reaction takes place, what is the concentration of cadmium, cadmium cyanide, and cyanide? Well, at this point I know 2 of them, almost. I can know the concentration of Cn-. Cn- comes from this guy. It's going to be 0.242 divided by the volume. What's the volume? Once these things get dissolved together, I have 500 milliliters, so that's 0.5 liters. And that is going to give me the concentration of that guy equal to 0.484. That's the molarity of the cyanide. How about the complex ion? Okay, to get the complex ion, the concentration of it is going to be this 0.00211 moles divided by its volume of 0.5 liters. Okay, and that is going to give me 0.00422. So now I know the concentration of that. I've got 2 of them, and the concentration of the cadmium is not really 0. And here's where the equilibrium comes into play. Let's plug the numbers in that we do know at this point. 3.0, actually we don't know it's 0.0, we just know it's 3, times 10 to the 18 is equal to 0.00422 divided by, I don't know, this is what I'm trying to find, it's not really 0, divided by this number, 484 to the 4th power. The cadmium is what I'm trying to solve for. It's going to be 0.00422. Bring this under 3 times 10 to the 18. This is already under 484 to the 4th power. And that will give me a cadmium concentration of 3 times 10 to the minus 20. Okay? So that is the concentration where this is not really 0. So you might say, well, if this isn't really 0, then that probably isn't really this concentration. That's not really this concentration. Well, it's really this much less than that. Okay? Subtract this from that, what do you still have? 0.484. Even if you do 4 times this, you have 0.484. It's such a tiny amount that it's not going to change those numbers, and that's the reality of it. I didn't really form all of this. I formed a teeny bit less than that. How much less? This much less. Okay, so it's not, yeah, it really is that number to that number of decimal places. So we now know the concentration of everything it asks for, I believe. Yep, everything it asks for in this problem. All right, so like I said, it's not complicated, except you've got to be able to write this reaction, and you've got to understand the nuances of how to solve it, and it only becomes complicated because you have a lot to keep straight. We're done with our equilibrium problems for now. Okay, we've done a wide variety. We did them in general, we did them for acids, we did it for bases, we did it for mixtures, we did it for insoluble salts, we've done it for complex ion formation, and that's enough.